And welcome back. As we go ahead and continue our conversation on recursion, let's go ahead now and bring in our conversation to discuss recursive stacks. So when we start talking about this term stacks, what are we referring to? Well, in order for a program or your computer to keep track of recursion, and among several other things that might be happening in your program, most computer systems use a structure known as a stack. A stack is a very specialized kind of memory structure that you can kind of think of as a sheet of paper or a stack of papers that are kind of put on top of another. So if we want to, for example, place information on the stack, it's written on one of these sheets of paper and then placed on the top of the stack of papers. So to place more information on the stack, a clean sheet of paper is taken, information is written on it, and then a new sheet of paper is placed on top of the stack, and so on and so forth as we move through it. So it's a pretty straightforward way of kind of thinking about how that information may be placed in a stack. And we're going to use this analogy as we kind of explore what exactly a stack is. The next thing you need to know is because of how things are put into a stack, they use this last in, first out structure. So getting information out of the stack is accomplished by a very simple procedure. The top sheet of paper on that stack is read, and when it's no longer needed, we throw it away. Now, of course, there's one complication. Only the top sheet of paper on that stack is accessible at time. I can't read in the middle of the stack, for example. I can't do the third sheet, right away because, of course, if I want to get the third sheet, I got to read the top two sheets first. And because that last sheet that is on the stack was the first sheet that we had taken, will be the first sheet taken off, it's called a last in, first out structure. So think of it this way: it's like just like if you were to pile things one on top of the other. You're going to deconstruct that list. You're going to have to start at the top and pull down. You can't pull from the bottom. All right, so it's last, whatever is the last one in is the first one out. Now we start discussing how this goes back to recursion. Using a stack, a computer can very easily keep track of how recursion is executed. So whenever a method is called, the way we can think about it is a new sheet of paper is taken. The method definition is then copied onto that sheet of paper, and the arguments are plugged in for our method parameters. The computer then starts to execute the body of the method definition, and when it encounters a recursive call, it stops the computation it's doing on that sheet to compute the value returned by the recursive call. But before, of course, computing the recursive call, it saves just enough information so that when it finally does determine the value returned by the recursive call, it can continue the stopped information. That saved information, of course, is then written on a sheet of paper and placed on the stack. A new sheet of paper is then used for the recursive call. The computer then writes a second copy of the method definition on this new sheet of paper, plugs the arguments in for the method, and starts to execute the recursive call. When it gets to recursive call within the recursive call copy, it repeats the process, solving information on the stack and using a new sheet of paper for the new recursive call. You might be noticing a pattern. This is very similar like when we start walking through our tracing. It's the same kind of idea. This process continues until some recursive call to the method completes its computation without producing any more recursive calls. When this happens, the computer turns its attention to the top sheet of paper on the stack. This sheet contains the partially completed computation that's just waiting for the recursive computation that just ended. So it's then possible to proceed with that suspended computation. When the suspended computation ends, the computer discards that sheet of paper, and the suspended computation that's below it on the stack becomes the computation on top of the stack. The computer turns its attention to the suspended computation that's now on the top of the stack, and so on and so forth. This process will continue until the computation on the very last sheet of paper has been completed. Alright, so let's start moving away from this idea of a sheet of paper and actually address how recursive calls are working. Depending on how many recursive calls are made and how the method is written, that stack can grow or shrink in any kind of fashion. So we could put some things on, get to a partial point, take some things off, put things back on, etc., etc. Now notice in our example we talked about the sheets in the stack can only be accessed in a last in, first out fashion. But if you think about it, this is exactly what's needed to keep track of the recursive calls so we know how we're handling them. Each suspended version is waiting for the completion of the version directly above it on the stack. So that gets us to things known as a stack frame or an activation record. And what is that? Well, computers, as we already figured out, don't use stacks of paper to keep track of things. All right, instead, we're using memory rather than pieces of paper. The contents of one of these portions of memory, which is of course our sheets of paper analogy, is called a stack frame, or otherwise sometimes known as an activation record. These stack frames are handled with the last in, first out manner we have already discussed. The stack frames don't necessarily contain a complete copy of the method definition, but merely reference a single copy of that method definition. So this is important to keep that in mind. However, a stack frame does contain enough information to allow the computer to act as if that stack frame does contain a complete copy of the method definition. Now, one thing to keep in mind when we work with recursion is stack overflow. There's always some limit to the size of the stack that you might be working with. If there's a long chain, for example, which a method makes a recursive call to itself, and that call results in another recursive call, and the call produces yet another recursive call, and so on and so forth, then each recursive call in this chain will create another suspended computation in place on the stack. If it's too long, the stack will attempt to grow beyond its limit. This is an error condition known as stack overflow. Our infinite recursion, which we already have explored, is an example of stack overflow. If you receive an error message that says stack overflow, it's very likely that one of your method calls produce an excessively long chain of recursive calls. As we already mentioned, infinite recursion, most common example to see this. Now, if a method is recursing infinitely, it will eventually try to make the stack exceed any stack size limit. So it's just going to keep going and going and going until, of course, we reach this error. Now, one thing we do need to discuss here as we kind of wrap up our introduction to recursion is recursion versus iteration. Because up to this point, most of our methods that we have been designing have been with iteration in mind. Recursion is not a required thing. In fact, it's even disallowed in some programming languages. Any text that can be written using recursion can be written some other way without recursion. And the non-recursive versions of methods, which we again are familiar with iterative approaches, typically are going to use a loop or multiple loops of some kind in place of using recursion. For this reason, the non-recursive version is typically referred to as the iterative version. Again, because we're iterating through a loop is the easy way to remember that. If the definition of the method, for example, right vertical, that we had in Recursion Demo 1 was replaced by the version we're going to look at now, which is a iterative version, the output is going to be the same. And that's because the recursive version method can sometimes be much simpler than an iterative version, as we're going to see, but it doesn't necessarily make it bad. All right, it might be a little more challenging to think about how you wrap your mind around it, but again, any way you can write a recursive method, you can write an iterative method, and vice versa. Now, there are some pros and cons to using recursion. A recursively written method is typically going to run slower because, remember, it has to manage all those stacks. And because it's managing all those stacks and using memory, it's going to require more storage than our iterative versions. The computer has to do extra work manipulating the stack to keep track of whatever recursion it's handling. However, because the system does all this for you automatically, using recursion can sometimes make your job as a programmer much easier, and can sometimes produce code that is actually easier to understand. And we'll see that when we actually look here in a second at those two different versions. So here we are, of course, looking at the right vertical method, and I have cloned it and just added right iterative here so we can compare them. And you can see we have the recursive and the iterative versions. If I run my code, of course, we get the exact same output. However, the difference is in how they're implemented. If you look at the recursive version here, you can see we have a simple if-else statement, we have a call to right vertical, and some print lines. That's it. If I look at how I do it with the iterative approach, though, you can see that there's a lot more here to handle. Not only do we have some integers that we're using to help keep track of things, we have a while loop that is looking to kind of handle the end piece of that. And then we also have a for loop, which is going to actually help us process out those other pieces that are in that remaining number. So if we kind of look at it, there's a lot to kind of really handle here from the iterative approach. But with the recursive, it's really simple. We don't have as much that we have to handle. We don't have as much to keep track of. Now, this is not always true. Sometimes the iterative version is a relatively simple implementation, and it's pretty straightforward that we can do that. But there are going to be times when recursion is going to be very beneficial because it's going to make things a lot easier to kind of analyze and approach.